Good morning, everyone. I will present today the result of our work on unidirectional spin-hole magnetoresistance in mercury telluride topological insulator. This work was made here in SpinTech for the experimental part and in close collaboration with the Nail Institute and the CLAT. So, over the past few years, three-dimensional topological insulators have attracted an increasing attention in the field of material science with their insulating bulk and conductive surface. The surface states are characterized by a large spin-orbit coupling leading to spin momentum locking, the spin being locked perpendicularly to the electron momentum. So if we take the point of view of spintronic application, this property is particularly promising as the aliasing effect can create a spin accumulation from a charge current in the surface state. And inversely, the injection of spin current creates a net charge current by inverse aliasing effect. So among topological insulator, the stained mercury telluride called AGT has the advantage of high mobility up to room temperature. Recently, in particular, we have demonstrated a large spin-to-charge conversion efficiency in this system up to room temperature, with conversion rate 1 order of magnitude higher compared to conventional material. So here, if we can achieve the mirror charge-to-spin conversion, that will be of great interest for memory and logic application. In view of memory, there is two effects in particular that can be exploited. The first is spin orbit torque, SOT, in which the spin accumulation induces a torque on the magnetization, which can be used as the switching mechanism in SOT MRAM. And the second is unidirectional spin-hole magnetoresistance, USMR, in which, depending on the relative direction between the spin accumulation and the magnetization, the system holds a high and a low resistance state. So while conventional SOT devices suffer from a three-terminal geometry, this USMR effect can be used as a new reading mechanism for developing a novel type of SOT MRAM with a two-terminal geometry. In particular, there is recent work that have shown the existence of USMR in T-high at low temperature. However, operating at room temperature will be a key requirement for practical application. In this presentation, I will present the results we obtained on unidirectional spin-hole magnetoresistance in AGT ferromagnet up to room temperature. I will first describe our development of ferromagnet with in-plane magnetization on AGT topological insulator. And I will then present the results we obtained on USMR together with spin-orbit torque effect up to room temperature. The AGT hole bar devices that we developed is shown here. The SAC consists in a 3.5 nanometer permalloy with in-plane magnetization deposited on top of a 30 nanometer AGT. So here there is a thin AGCDT barrier that is used to protect the T-high surface state from direct contact. For harmonic measurement, the stack is processed into microscale double hole bar devices for electrical measurement. On the left, the temperature dependence of the sheet resistance shows dominating metallic transport, which corresponds to the conduction in the metallic permalloy along with the AGT surface state. On the right, the in-plane magnetic field dependence shows the magnetoresistance of the permalloy layer around 0.4%, confirming the in-plane magnetization of the ferromagnet. So in which follow, we perform harmonic measurement of the longitudinal and hole resistance to investigate spin-hole magnetoresistance and spin-orbit torque effect. The figure below shows the first harmonic resistance during rotation of the applied field in the X-Y and Y-Z plane. There is a sizable magnetoresistance that is observed in all three orthogonal planes with the Y-Z magnetoresistance ratio of 0.52%. The resistance measured when the magnetization is saturated along the Z and the X direction is larger than along the Y direction, which confirm a typical SMR-like behavior. Now, to probe the presence of USMR, we measure the second harmonic longitudinal resistance as the function of the magnetic field in the y direction. Shown on the bottom, the results show a change in the nonlinear magnetoresistance upon switching the magnetization from plus y to minus y direction. This change here of magnetoresistance is the signature of USMR driven by LSN effect. Now, to extract the USMR efficiency, it is necessary to take into account the influence of thermal gradient as the anomalous Norris effect and the spin-Seebeck effect, which can also give a second harmonic component. For that, we measure the second harmonic transverse Hall resistance when the magnetization is tilted, but in the x direction. So because of the symmetry, the transverse Hall resistance gives the second harmonic signal of thermal origin simply scaled by the geometric factor of the Hall bar. Shown on the right, the results show a small change in the nonlinear magnetoresistance upon switching the magnetization from minus x to plus x direction. So this change corresponds to a combination of thermal effect along with spin-orbit torque effect. Since the thermal effect is very small, we make a first-order estimation of the USMR efficiency by neglecting the SOT contribution, yielding 2.6 ppm per ampere centimeter. So this USMR efficiency is 3 times higher than in ferromagnet normal bilayer and on the same order of low-temperature bismuth-like topological insulator. So here, importantly, we demonstrate unidirectional spin-hole magnetoresistance in mercury telluride topological insulator. As seen in the figure below, USMR increased linearly with the current density and converged to 0. This is a signature of the unidirectional nature of USMR in IGT topological insulator. Given the high mobility in IGT up to room temperature, we repeated the same USMR measurement but for different temperature. The experimental result at room temperature show comparable USMR efficiency with nearly temperature-independent USMR. So here, importantly, we demonstrate the highest USMR efficiency to date at room temperature, and we made the first demonstration of USMR up to room temperature in topological insulator. So last, we are also interested in the current-induced spin-orbit torque effect. So as shown here, the second harmonic transverse Hall resistance is composed of a thermal contribution and a spin-orbit torque contribution, anti-damping-like and field-like component. So regarding the angular dependence, the field-like torque has a cosinus phi plus cosinus 3 phi dependence and thus can be separated from the thermal and anti-damping-like contribution that both have cosinus phi dependence. The anti-damping can be further separated from the thermal contribution by considering that it induces a dynamical oscillation of the magnetization and hence decrease with the amplitude of the magnetic field. Shown on the bottom are the angular dependence of the second harmonic resistance in the x-y plane with a current of 1 mA for different applied magnetic field. The results show a strong angular dependence that increases with the magnetic field. So this strong signal is characteristic of an intrinsic property of mercury telluride topological insulator that is called the bilinear magnetoresistance BMR. As seen on the top figure, the second harmonic longitudinal Hall resistance is actually composed of 2 components. The first is the step part around the zero field that corresponds to the USMR of the mercury telluride ferromagnet system. And the second is a linear background, which corresponds to the BMR of the AGT alone due to symmetry breaking at the surface states of the TI. So we are currently investigating this BMR effect, which must be quantified to properly decorrelate the spin-orbit torque effect from the BMR effect. To summarize, we have developed ferromagnets with in-plane magnetization on AGT topological insulator. Unidirectional spin-hole magnetoresistance was observed with efficiency 3 times higher than in ferromagnet normal bilayer and on the same order of low temperature bismuth selenide topological insulator. So here, importantly, we demonstrate the highest USMR efficiency to date at room temperature, and also we made the first demonstration of USMR up to room temperature in topological insulator. So this is an important step toward SOT-MRAM at room temperature with two-terminal geometry. Now, to go further, more material development can be made to improve USMR efficiency and SOT efficiency, together with the development of perpendicular magnetization for achieving current-induced switching. Also, it will be very interesting to develop a backgate for electric control of both the USMR and the SOT efficiency. So with this, I would like to thank you for your attention.